कैमरा साफ कर देते हैं थोड़ा। $11:30.
M prime. So we have to design M prime given M comma W. Okay, so this is what we have to do. So we take as input M comma W, and then we give a construction of M. So design a Turing machine M prime that on any input X does the following. So before I give the description of M prime, let me say something. So we just saw that there exists a Turing machine M whose language satisfies the property. So we saw this existence, and we said that this Turing machine, we called it as M. So what we will assume here is that the Turing machine M prime that we are going to design has a copy of M hard-coded into its description. Of course, it has M.
सब इतना ककड़ा बना देते हैं, इतना मुश्किल तरीके से समझाएंगे ना, मैथमेटिक्स घुसा के फंक्शन घुसा के ऊपर तंग करते हैं आप। तो जब मैंने बिल्कुल सिंपल वे से समझाया, आपको समझ आया मैंने क्या किया? m, w था ना भाई, पहले मैंने m, w ओरेकल ट्यूरिंग मशीन को दिया, जो मैंने जादुई ट्यूरिंग मशीन बनाई थी ऑल्टी प्रॉब्लम को सॉल्व करने के लिए। तो वो m को वो क्या बताएगी भाई, w अगर m एक्सेप्ट करता है या नहीं करता है, मतलब सॉरी होल्ड करता है कि मतलब while प्रोसेसिंग w m will hold or not। अगर m हमारी होल्ड करती होगी तो ये आंसर यस देगी, और अगर होल्ड नहीं करती होगी तो आंसर नो करेगी। अब अगर आपने अगर ओरेकल ट्यूरिंग मशीन ने आंसर नो किया, मतलब होल्ड नहीं करता तो ऑब्वियस बात है रिजेक्ट ही है, वो मोस्टली हमारा रिजेक्ट है ना, तो हम रिजेक्ट वाली बात पे आ जाएंगे, मतलब नो पे आंसर आ जाएंगे। अच्छा, और अगर ये ओरेकल ट्यूरिंग मशीन हमारा आंसर यस करती है, इसका मतलब होल्ड कर रही है मशीन, है ना, तो मतलब व्हाइल प्रोसेसिंग w m will hold। अगर m will hold होगी तो मैं क्या करूंगा, अब जो अपना मेरा w था वो मैं इस m पे चला दूंगा। m पे चलाने के बाद आंसर अगर यस आ गया तो मैं क्या बोल दूंगा कि हाँ दीजिए एक्सेप्ट हुआ अभी, तो हम आंसर यस बोलेंगे, हमारी बड़ी वाली मशीन आंसर यस बोलेगी। अगर इसने नो बोला कि मतलब मैं एक्सेप्ट नहीं करती, तो ये आंसर नो कर देगी। तो अब आप मुझे ये समझाओ, मैंने एक बड़ी मशीन बना करके दिखा दी ना भाई, क्योंकि आंसर यस और नो दोनों दे रही है, तो एल्गोरिथम आ गया ना। तो आपने क्या बोला कि जो हमारी ये मेंबरशिप प्रॉब्लम है, एलयू वाली जो प्रॉब्लम थी, दैट इज डिसाइडेबल। बट आपको पता है कि मेंबरशिप प्रॉब्लम डिसाइडेबल नहीं है, तो जो आपने क्लेम किया कि हमने ये कोई जादू ट्यूरिंग मशीन बनाई है हॉल्टी प्रॉब्लम को
एक्सेप्ट करती है,
हॉल्टी प्रॉब्लम के लिए हमने यस और नो निकाले, जो जादू ट्यूरिंग मशीन बनाई थी वो सब बकवास है, मतलब कोई ओरेकल वगैरह सब बकवास है, कुछ नहीं एग्जिस्ट करता। आई थिंक समझ में आ गया होगा सबको मैं क्या कहने की कोशिश कर रहा हूं। ठीक है जी, ऐसे ही अब देखो मैंने तो ये चीज दिखाई है ना आपको, जैसे कॉम्प्लीमेंट ऑफ मेंबरशिप प्रॉब्लम ऑफ आरई भी ट्यूरिंग रिड्यूस। देखो अगर अपने वाला भी आंसर कर याद आ रहा है कि नहीं आ रहा भाई, तो पाऊंगा इसको होगा, तो इसे ट्यूरिंग मशीन बनाने पाऊंगा, क्योंकि अगर एक्सेप्ट नहीं हो तो एक्सेप्ट को मतलब कॉम्प्लीमेंट ऑफ वैल्यू याद है ना भाई, कॉम्प्लीमेंट ऑफ मेंबरशिप प्रॉब्लम हमारी मतलब गिवन स्ट्रिंग w याद आ रहा है कि नहीं आ रहा भाई, m, w। तो क्या इस w को प्रोसेस करते टाइम हमारी मतलब यू कैन से m क्या एक्सेप्ट होगा w से, दिस इज द क्वेश्चन। lu क्या कहता था कि ये w क्या m से एक्सेप्ट होगा, क्या w m से एक्सेप्ट होगा, दैट वाज lu। और LU बार क्या थी भाई, कॉन्फ्लिक्ट ऑफ मेंबरशिप प्रॉब्लम, क्या WM से एक्सेप्ट नहीं होगा, दिस इज द क्वेश्चन। ज्यादा लेके नहीं आ रहा, तो ये यस इंस्टेंस है ना, वो सारे वन हमारा LU था, और जहां जहां जीरो थे वो सारा LU बार।
Machine must accept this X, but this machine will start if and only if
राइसिस थ्योरम का प्रूफ कहाँ मिलेगा? हम लोगों को कैसे पता चलेगा राइसिस थ्योरम का जो प्रूफ है ना?
अरे कृष्णा, अरे ये आपकी उंगली ये
3 a.m. And here, so I want to apply Rice's theorem to this language, which is called an ETM, which is called the emptiness for Turing machines problem. And here we have a set of descriptions of Turing machines, such that that is a Turing machine, obviously, and the language of that machine is empty. And the ETM problem is to ask, given an arbitrary Turing machine, is it in this set right here? Is it one of these Turing machines? And famously, it's an
बेटा ये जो टन था ना, ये किस कंपनी का था?
टन ही तो है कंपनी, एसएस टन।
एसएस का।
टन ही तो है, मतलब
टन तो ये है
शायद
एसएस कंपनी।
हाँ, आपको तो ज्यादा पता है इसमें के बारे
एसएस से गोया इसने, फिर मैंने इसको डांटा ना, इसने 15 दिन पहले फिर एसएस के चंडीगढ़ भेजा था बैठ। और क्या, ऐसा थोड़ी होता है यहाँ। ये कैसे हो गया 15,000 की चीज को? तब वो आ रहा आज शाम तक।
आज शाम तक आएगा।
कहता है
डिफेक्टिव, बैड लक था, क्योंकि
नहीं, हैंडल वो मैन्युफैक्चरिंग डिफेक्ट होता है कभी
होता है
कभी।
कभी कभी। अब वो आपको मैथ्स अभी भी याद है?
कौन सा मैथ?
अरे सिंपल मैथ्स, कुछ ये मेरे को समझ में नहीं आया, मैं आपसे ही अब ये पूछूंगा।
बोलो कौन सा
ये
अरिथमेटिक है, अलजेब्रा है?
देखो ये
बोलो, जूम तो करो ना पहले।
इसका क्या मतलब हुआ? P of phi is equal to 0।
चलो चलो, पी एफ, ये तो डिफरेंशियल कैलकुलस है, सुना? डिफरेंशियल कैलकुलस पढ़ी है तुमने?
नहीं, आज
पढ़ी
तक
थी,
हाथ
पढ़ी
भी
थी।
नहीं लगाया।
पढ़ी थी थर्ड में, जो मैथ किया है ना, वो क्या नाम है उसका, जो था थर्ड का मैथ, जो तुझे वापस था, क्या नाम था उसका?
थर्ड का डिस्क्रीट मैथ्स।
डिस्क्रीट मैथ्स।
अच्छा 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 अच्छा, ये डिस्क्रीट मैथ्स का है।
हाँ, तो बादशाह
ये एजम्पशन हर जगह लेनी है, ये मतलब हर एक प्रूफ में ये एजम्पशन ये दिया है, केस 1 P of
P phi is equal to 0। phi क्या है? What is phi? Phi is a set of
empty set।
empty set। हाँ,
अब मगर फिर भी ये कुछ समझ में नहीं आ रहा है।
P प्रोग्राम empty set का है, कुछ भी नहीं है वहाँ, खाली है, 0 है। P phi is equal to 0 is 0। यानी कि कोई भी चीज, इसको आप न्यूमेरिकल नोटेशन ऑफ मैथमेटिक्स में रिप्रेजेंट करते हैं। ये तो तूने
अच्छा, ये देखो इसने एक और यहाँ पे दिया है, बहुत अच्छी एग्जांपल है। अ प्रॉपर्टी P इज नॉन ट्रिवियल एंड phi बिलोंग्स टू P।
यस,
ये इसने
phi belongs to B। गो P का एक जो आपकी प्रोग्रामिंग है ना, ये सेट थ्योरी पे ही सारा डिपेंड करता है।
अच्छा,
जो आपका लॉजिक है, सेट थ्योरी, आपका कंसेप्ट क्लियर है?
वन लैंग्वेज सेटिस्फाइज P। अच्छा अच्छा अच्छा, सुनो अबू,
ये सेट, तुझे पता है वो सेट थ्योरी तू पढ़ा करता था?
अच्छा अच्छा,
सेट्स, यूरी, इंटरसेक्शन, उसमें क्या क्या है, कॉमन क्या है, या ए यूनिवर्स बी, ए इंटरसेक्शन बी, याद है तुझे?
हाँ,
उसी के रिलेटेड है, ये इतना ज्यादा मुश्किल नहीं है।
इतना ज्यादा मुश्किल नहीं है। ठीक है ठीक है ठीक है। बाप रे बाप।
This is the TM. Then what? similar to blunt language.
अब ये पता है क्या बोल रहा है? ये बोल रहा है P is non-trivial. For example, एटलीस्ट वन एलिमेंट तो होगा. अगर किसी चीज की कोई प्रॉपर्टी है किसी सेट की, तो उसमें एटलीस्ट वन सिंबल तो होगा. एटलीस्ट एम्प्टी सेट तो होगा. अब इसको पता नहीं है कि कौन सा सेट होगा, क्या एलिमेंट होगा, ये इसीलिए एम्प्टी सेट ले रहा है.
So here, with set of set, so the like, whatever. Say during property M is an empty language.
एक सेकंड, क्या?
Right? So we prove the theorem in two parts, in two cases. So case one,
Non-trivial properties and
consider the language phi,
अच्छा 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 अच्छा.
empty language. So at of
वो ये भी तो है नॉन ट्रिवियल प्रॉपर्टी.
so if we assume that p of phi is 0, then what we can say is that since such that there exists a Turing machine, such that the language of, so there exists a Turing machine, let's call it N, such that the language of N satisfies the property, or in other words, P of L of N equals 1. So here we have a language which does not satisfy the property. So that means that there must be some other Turing machine.
ओके 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 ओके. ओ नहीं नहीं नहीं.
whose language satisfies. And of course we can construct a Turing machine whose language is empty set. Okay, so we just have a Turing machine which
Whose-
rejects all inputs.
All
We of
inputs.
course
Okay.
have a Turing machine for phi. So now, so using this Turing machine, we will prove that, so using this, we will show that ATM reduces to LP. So recall that ATM is undecidable, so this will prove that LP is undecidable. So what is the reduction?
यार दिमाग में आ ही नहीं रहा कुछ ये वाला हिस्सा. Suppose a property P is non-trivial and phi belongs to P. Since P is non-trivial, at least one language satisfies P, that is LM naught of P belongs to P. Turing machine M naught. ये क्या बना भाई मेरे? मुझे कुछ खास ये concept नहीं लगा इतना. ये कुछ बहुत ज़्यादा अजीब सा है. Contradiction is थोड़ा सा difficult यार. ये न्यू लग रहा है, अलग सा weird सा. Let W be an input in a particular instant and N is a Turing machine which follows. On input X, run M on W. If M does not accept, then do not accept X. Accepts, then run M naught on X. If M naught accepts X, अच्छा अच्छा अच्छा. ATM is undecidable, it can be reduced to LP.
The property is not possessed by because P is non-trivial, right? So here we are taking P having the property. So P is a property that is non-trivial. So P is a non-trivial property, and the language that holds the property is, we are calling it L of P. So the language of machines that holds, or all the machines property as this is undecidable property. Right? This is undecidable property. Brain and they breathe. So these properties can be possessed by all the human beings. Okay, so we are categorizing these properties on the basis of these, on the basis of this example. We can categorize the properties of languages, the properties that can be possessed by all the machines, or cannot be, or by the none, or by some machine, but not by all. So we can categorize these properties into two categories as trivial property and non-trivial property. Now, what do we mean by trivial property? A property that holds for every machine, okay, or holds for none is trivial. If we say the every living being is having brain, and every living being breathes. So these properties are trivial properties. Trivial properties because every living being is having the breathing property and having the they also have the brain. So we can say that these properties are held by all, or there may be some property that may be held by none. So these type of property either hold by all or by none. So we call such properties as trivial properties, right? Now the second category is non-trivial property, the property that is neither true nor false for every computational function. Okay, so if we cannot be sure that the property is possessed by all the machines or not, then we can say that property as non-trivial property. For instance, we cannot be sure that every program will term excited property. This theorem doesn't apply to the trivial property, and Rice's theorem is all about to prove that non-trivial properties are undecidable. Non-trivial properties are undecidable. We cannot predict whether the non-trivial property will be possessed by all the machines or not, and this problem is undecidable. So Rice's theorem just proves this concept by, we will be proving this by a simple contradiction, by just reducing the problem to a single machine, and then we will prove that the problem is undecidable with the help of universal Turing machine. So let's start with the Rice's theorem. So these are the non-trivial according to the properties that we have covered. These properties are the example of non-trivial properties, and this last is the example of trivial property, because we can say that every machine will only accept the combinations of strings that are subset of input symbols. Okay, so every combinations of the acceptable strings are subset of the combinations of input symbols. So only this property is trivial, and rest of these properties are non-trivial, because we cannot be sure of these properties for all the machines. We cannot say that these properties will be possessed by all the machines. So these are the non-trivial property, and this is the trivial property. Like every human being breathes is a trivial property, and every girl is having long hair is non-trivial property, right? So Rice's theorem is all about non-trivial property and prove that non-trivial property is undecidable. Next we have Rice's theorem. So just we are having a brief discussion about the examples and what we have to prove with Rice's theorem. Now coming to the definition, any non-trivial property about the language recognized by a Turing machine is undecidable. So this we have to prove that for a Turing machine we cannot say that the non-trivial property will be possessed or not. So this problem is undecidable. Okay, and this theorem is named after the Henry Gordon Rice, who proved this theorem in his doctoral dissertation of 1951. Right? So the problem, halting problem like this. So here we cannot say that like halting problem like PCB problem, we cannot say that there exists or there may exist an algorithm or a machine that can predict whether the Turing machine will hold this non-trivial property or not. Okay, so such type of machine, like for halting problem, we were assuming that a machine exists that can predict whether the machine will halt for a particular input or not. And for PCB problem, we were predicting the machine that can give the output as the PCB is solvable or not. So for this Rice's theorem, we cannot have such machine that can take the description of a machine and the non-trivial property as input. So this P is representing the non-trivial property, and such machine, we are assuming that such machine should predict whether this property is possessed by this Turing machine or not. But in practice, there is no machine that can always decide whether the language of a given Turing machine holds a particular non-trivial property or not. So we cannot have any such machine that can predict whether this non-trivial property P will be held by this particular Turing machine or not. We cannot practically have any such machine. So we have to prove this with these steps as this we have already discussed. Rice's theorem states a non-trivial property, and by property we mean that the language of all Turing machine that satisfies that property. So language of all the Turing machine that satisfy the particular property P, right?
Rice's theorem states that any non-trivial semantic property of a language which is recognized by a Turing machine is undecidable. A property P is the language of all Turing machines that satisfy that property.
So here, if P is a non-trivial property, for proof we are taking P as one of the non-trivial property that we are taking as example, and we will be proving that this property is non-trivial. Right? So here we are taking P as non-trivial property and the language holding the property. So P is a property that is non-trivial. So P is a non-trivial property and the language property is possessed by all the machines M, all Turing machine M is undecidable. So we have to prove that this statement, this language is undecidable. We cannot write such language, means we cannot be sure of all the machines. Suppose this property is possessed by M1 and also by M3, but not by M2. So if we have any such machine that doesn't possess this particular property, so the property is not trivial, the property is undecidable and non-trivial, because all the machines are not possessing this property, right? So the proof starts with first step as let P is a non-trivial property, right? We have already covered this, and as P is a non-trivial property, so it is not possessed by recursively enumerable language L. So we are taking an assumption that this property is not possessed by recursively enumerable language L, and for this language L we are having M dash as a corresponding machine. So this is our M dash, the corresponding machine for this language. The machine that accepts the strings of this language is M dash, and the property is not possessed by M dash, right? Now second, we are taking the problem can be reduced. So we are taking that problem can be reduced to a smaller problem by taking a universal Turing machine, and we are saying that this universal machine is possessing this property if and only if this machine can accept this input string W. So we are reducing the problem, means the problem of non-trivial property, we are reducing it to simple. This Turing machine and the set and one input string W. So if this universal Turing machine, this UTM with language L of U, so this universal Turing machine is having language L of U. So if this machine accept W for this M, so universal Turing machine can perform the task of any machine, and we need just to provide the description of the machine and the corresponding input, and the universal Turing machine will give the output, right? So if this universal Turing machine can accept this W for this machine M, then we can say that the property P is possessed by
recursive.
The machine, right? So here thus we take UTM-U that takes the pair this, the description of a machine and the input string as input, and output yes if and only if the P, the non-trivial property, is possessed by L. If this property is possessed by L, then we can say that, only then we can say that the property is possessed by the language L. Otherwise, if the W is not accepted by the machine, the property is not possessed by the language, right? So here we have reduced the properties possession problem with the simple problem of accepting a string by the machine M, right? If the machine is accepted by this UTM, then the property is possessed, otherwise the property is not possessed by the language. So last, thus there must be a machine M of L. Now if the property is possessed, means if this W is accepted by this machine M, then the property is possessed. So we are taking a contradiction here. The property is possessed by this machine, this language, and if the UTM, universal Turing machine, is accepting this and property is possessed by this machine, then this is giving a yes, and after this yes we are again starting a new machine. We are starting a new machine, that is M of L. So now we are running the machine M of L corresponding to this language